Here's a bit of review of what we've been doing so far. So I have here a positive 2 microcoulomb charge, and we're sitting at a field point location 75 centimeters to the right or east. Caleb, what does A want me to find?
Electric field.
Electric field. Did it say electric force?
No.
Did it say energy? And the reason I'm going to start to do that is you're going to notice after today we have a whole bunch of equations that look identical, and it is incredibly easy to get these equations mixed up. I love the fact that Caleb has his formula sheet out. I hate the fact that some of you don't have your formula sheets out. You probably want to have your formula sheets out. I'm just saying. Caleb, what does it want me to find?
Electric field.
Now, what letter do I use for electric field? You might be tempted to say, well, it's field. Don't I use F? What letter is capital F reserved for? What concept is capital F? Force. So please don't do that. So what letter do I use for electric field?
E.
Okay. So that's the first thing if you want to identify which equations we're going with. They want me to find E. There's a problem. There's 2 ways to find electric field from your formula sheet. See them both? Mm-hmm. One way is K big Q over R squared, and one way is F over little q. Which method am I going to use to find electric field here? The first one or the second one? First one. How do I know?
Because it gives you an R.
Gives me an R. Okay? If it was the second one, Kyle, they would have had to tell me the actual force at that location and how big the charge at that location. Little q is the orbiting satellite charge, not the big planetary charge causing the electric field. That's also important because I'll guarantee I'll be asking you both versions on your test. All right. Caleb, what's K? No. Sorry. Lyndon, what's K?
9 times 10 to the 9.
Good. Caleb, what's Q?
2.
Let's do me a favor, folks. Look up. Let's make this a negative. Do I put the negative in here?
No.
What about for forces? Look at your sheet. What about for forces?
Yes. No.
How do you know?
There's absolute value.
What about for energy?
Yes.
Yeah. By the way, we haven't done it yet, but what about for V voltage?
You need to put the negative.
Yeah, you can have a negative voltage. Okay. So I'm not going to put the negative into my equation. It's going to affect the direction. So 2 microcoulombs and 0.75 squared. What's the magnitude? Crunch this on your calculator, please. Little reminder, we said electric fields are typically, not always, but typically in the thousands, tens of thousands, once in a while in the hundreds of thousands. But if you get something with like a 10 to the 12th, or if you get something with like a 0.06 for electric field, you probably messed up. What'd you get?
32,000.
Caleb? 32,000? Even? Units. Can't remember. It's on your formula sheet in disguise. The second, I think it's the second equation, Caleb, for electric field tells you what the units have to be. Because what's on top in the second equation?
FE.
Which force is measured in? Per. What's on the bottom?
Q.
Which is measured in? I thought I heard it there. What? Coulombs. Okay? So the units must be newtons per coulomb. Direction, because electric field is a vector. How do we define the direction? We don't use like repel, unlike attract. We said we define the direction by asking which way would a positive at this location right there want to move if it could? Which way will a positive charge sitting right there want to move? Towards or away?
Towards.
Okay? So now, if I get rid of the negative, cross out the negative, this number wouldn't change. This number wouldn't change. We'll go back to the actual original question. Direction. Which way would a positive sitting right there want to move if it could? So we would call this east or right. That's electric field. What if we had more than just one charge? We would find each electric field separately, magnitude and direction, and then we would add them vectorially by going winner minus loser if they were in a nice straight line, tip to tail if they were not. Braden, what's B want me to find?
The force on
A 1 coulomb charge, a massive charge. 1 coulomb is pretty big, placed at that point there. Okay, that's going to be K Q1 Q2 over R squared. Wait. Write that down. And then just really lightly cross it out. Let's be clever. You've had me for a couple of years. What letter is next to this question? This is part what? What did we find in part A?
the electric field.
Is there an equation that has electric field and force in it? Is there any way maybe I could use part A as a shortcut? There is? Oh, so I could fall back on that if I needed to, but let's be clever here. What's the equation that has electric field and force in it? Stop, get the F by itself.
E times Q.
Another way to calculate electric force, I'm going to write it as QE, and the only reason I'm doing it that way is I'm trying to make it look like little m, little g for gravity, because G was gravitational field and E is electric. I'm just trying to make it look symmetrical, okay? If you wrote EQ, I'm not taking marks off. I'm just trying to tie it into all stuff we already know. So we got a nice shortcut here. In fact, I'm going to bet you that Braden can even do this in his head, because what's Q, the charge at this location, according to part B?
1.
Oh, really?
Yeah.
And what was the electric field?
32,000.
In your head, without a calculator, what's 1 times 32,000?
32,000.
Now, what would our units here be? It's a force. And then direction. So we put a positive charge right there of 1 coulomb. Which way is it going to feel a force because of that 2 microcoulomb charge? Also to the right, because the electric field tells us which way a positive would want to move, and the charge they gave us was a positive. How would I do part C? I'm going to skip it, but you know what? I would go QE again. It would be 2 times 62,000. It would be, times 32,000. It would be 64,000 newtons to the right. So one of the nice things, one of the things that electric field is helpful for is the same way for gravity. If you knew little g, it was a big shortcut. You didn't have to go big M, little m over R squared. If you happen to know the electric field, it's a nice shortcut. You don't have to go big Q, little q over R squared. Let's just do D. Again, it wants us to find the force. Again, it's going to be QE. So it's going to be 1 milli, which is 10 to the negative 3 times 32,000. I think 10 to the negative 3 mathematically is the same as dividing by 1,000. So Braden, in your head, 32,000 divided by 1,000. I think it would be 32 and newtons. And is the charge they gave us positive? In part D? Yeah, okay, so that would also feel a force to the right. So we figured out the direction, Nate, in 2 different ways. We could have figured out the direction of the force using like charges or unlike charges. Like charges repel, in this case. Or I could have said, since I know the direction of the electric field, I know which way a positive will want to move. If they'd given me a negative, I would have just said, oh, the direction's got to be to the left. Okay? So we're tying a lot of little details together there, Eric. I hope that kind of clarifies things. Okay. The electric field tells us how many newtons of force per coulomb at a location. I need you here because now we're going to define voltage. So ignore the distraction. Yeah, I'm looking at you. For energy, there is a similar concept. Instead of telling us force per coulomb, it tells us joules per coulomb. How many joules of energy every coulomb of charge has. This is called potential. I prefer the term voltage It's also called voltage. The reason I prefer the term voltage is, listen to this sentence. Potential tells you how much potential energy per coulomb. Potential and potential energy are not the same thing, and you can't get them mixed up, but they both have the word potential. I know. There's potential to mix up potential and potential energy. But I will most of the time gravitate to the word voltage, but in your homework and in your package and in your notes, the word potential will show up. And I also know, having read a few electronics manuals, they prefer the word potential. And I kind of know why. I just find it confusing because it's easy to mix up potential and potential energy. But what's the definition of voltage? It's the amount of potential energy every coulomb of charge at a location has. And I believe that's on your formula sheet. Yes? Yeah. That's the definition of voltage. Oh, by the way, what would its units be? What do I measure energy in? Joules. What do I measure charge in? Coulombs. So it's joules per coulomb, but we give this a special name. Do you know what the units for voltage is? It's volts. Okay? So a volt, if you break, you've already noticed, like newtons is actually meters per kilogram, meters per second squared. A lot of our units we can break up into smaller. Joules was actually Newton meters because it was force times distance. Power is measured in watt? Watts, which was a joule per second. Volts is a joule per coulomb. Okay. We're going to go one step further, though, and try and come up with an equation for voltage. So example 2 says, fill in the proof to find the potential, not potential energy, or voltage due to a point charge Q. Here's what we're going to imagine. We're going to imagine that we move a test charge little q to a field point and then find the ratio of the potential energy per charge. Say what? What was our equation yesterday from potential energy? K, big Q. So voltage, since it's the amount of energy per little q test charge, I guess is going to be K, big Q, little q over R, all divided by little q. And Lena, what you're hopefully going to notice is, and this is your second equation for voltage on your formula sheet. There's one equation where I actually define voltage. It's energy per coulomb. And then you should see another equation that looks like this. K, Q over R. Is that okay, Sarah? Put your pencils down, look up. What's that? We just did it. What is that? Also called? This is potential. Look up. Potential energy. Look up. Force. Look up. Electric field. And if you don't think it's easy to get those four equations, you're nuts. Oh, and just for giggles, I've given you potential and potential energy. Ha ha! And here's my big concern. I guarantee on the test, I will ask you to find the electric field. I guarantee I'll ask you to find the potential energy. I guarantee I'll ask you to find the potential. I'll ask you to find the force. And my big concern is, supposing I say the most common mistake, find the potential, and you find the potential energy, I have to give you 0 on that question. I can't even give you part marks because you haven't even started the first step correctly, and you may have found the potential energy correctly. It's like, it's not what I asked you for. It's as though I said, find the acceleration, and for giggles, you found time. I'm glad you found time. Good for you. It's not what I asked for. Can't even give you part marks. So, this is the reason I've been yelling at you all the time. Get your formula sheet out. Look at where they are and try and train your eyes to look in the right location. Okay? So this also is volts. KQ over R, or potential. Big Q is the planetary charge that's causing the voltage. So I would use this one if they give me a big charge and the location. In other words, remember the very, very first question we started with for electric field? I asked you, which equation do we use? And one of you said, I think it was you, use the one with the R in it because they gave us an R. If they give you an R, use this one. If they just give you a location and an energy amount, use that one. Little q, it'll be the satellite orbiting charge. Turn the page. This is exactly the same question that we did, except, Caleb, what are they asking me to find?
The potential.
What's in brackets? I'm going to stop eventually putting that word in brackets. I'm just going to say to you, Kieran, you'll have to read very carefully. Potential is voltage. Potential energy is joules. How am I going to find the voltage? Once again, there's two equations. There's this one, energy per coulomb, and there's this one. Which one am I going to use? How do I know? Because they gave me an R. Okay. So it's going to be 9 times 10 to the 9th. Lyndon. And charge. Now, put a negative here temporarily in front of the 2. Put a negative there temporarily in front of the 2. Can I have a negative voltage? Oh, heck yeah. It's going to be negative 2 microcoulombs all over 0.75. What do you get? Voltages typically will be in the hundreds or in the thousands or in the tens of thousands. Rarely in the hundreds of thousands. Yes?
Why is it a negative?
Because I just wanted to show you that we include the signs because this one is a scalar and doesn't have absolute value signs around it. It doesn't have absolute value signs around on your formula sheet, does it? So here you're going to include the sign. Negative 24,000. Direction. Energy, scalar or vector? Scalar, no direction. Charge, scalar or vector? It's a scalar, no direction. No direction divided by no direction gives, much like your futures, no direction. It's a scalar. Voltage is a scalar. Also, I knew it was a scalar because we included the negative sign here. If it was a vector, we wouldn't have put the negative in. We would have used the negative to figure out a direction. Braden, what's B want me to find? Oh, potential energy. Oh, that's easy. We did that yesterday. It's K, big Q, little q over R, not R squared. Oh, wait. You know what? Write that down, but then really lightly cross it out. Do you? Braden, what did we find in part A? Is there an equation that has voltage and energy in it? There is? Really? Could you read me that equation, but do me a favor, get the energy by itself, please. So you're telling me another way to find energy is QV? This is where voltage can be very handy. If you happen to know the voltage at a location and you're finding a bunch of different amounts of energy, it's a nice shortcut. In fact, I'm going to argue that even Braden can do this in his head. Braden, what's Q in part B? 1 coulomb. Our voltage there was that. And so we get negative 2,400 joules. Now, what does that mean? This charge is negative, and right now we just put a positive, we put a big positive charge right there. Which way does it want to move? Towards. If I want to move it out to infinity, I have to add 24,000 joules to that negative 24,000 joules to get to 0 out at infinity. I would have to do work. It does not want to go out to infinity. It wants to fall closer to that negative charge. Skip C. Let's do D. Braden, what does D want me to find? And you know what? I could go Q, K, Q1, Q2 over... Wait. Do I know the voltage at that location, at that field point?
Yes.
Well, then, heck, I have a shortcut. Also, potential energy is QV. Now, you're going to start to notice, without me thinking about it today or tomorrow for sure, look up, I'm going to start to make my voltage V's with little wings on them. And the reason is voltage is a capital V. What's a lowercase v, our symbol for? We are going to have questions that have velocity and voltage in them, and when you handwrite, it's often difficult to tell the difference between an uppercase and lowercase v, especially since I don't give you lined paper. So I'm stealing something that I stole from my first-year university prof. He always said if you want to show something as a capital letter, put like the little serifs they do in type font on there. So my capital V's are going to have wings on them. I'm going to start to do that without even thinking about it all the time. Because to me, writing voltage without that without the wings is fingernails on the blackboard, because I'm going to get it mixed up later for a velocity and I want to do that. So I'm doing that now. Okay? What was little q? 1 microcoulomb. And the voltage at this location was negative 24,000. Brayden, can you do it in your head?
Negative 2.4 times 10 to the -2.
Caleb, in your head?
Negative 24.
Can you move your hand away from your mouth?
Negative
And
24.
before you say it, you're going to look at Brayden and you're going to shake your head while you're saying it in pity.
Negative 24. I'm trying to put it wrong.
Joules. Direction, energy is a scalar. What does that tell us? That means if I did put a 1 millicoulomb charge, a positive 1 millicoulomb charge right there, I would have to do 24 joules of work. I would have to add 24 joules of my energy to get it out to zero at infinity. Okay? I'm also hoping this is kind of tying a lot of loose ends together. I hope. All right, let's kick it up a notch. Oh, sorry. So, another concept is potential difference, or the change in voltage. What's change in anything? Okay. We have a special name for that. The potential difference is what we call it, the change in voltage. Then we can find the work required to move a charge between these 2 points. Last day we found the work, and we had to use ditto marks and all that garbage, which works. But I'm telling you, if you happen to know the change in voltage, you got a nice shortcut. Example 4. They used to love throwing this picture on the provincial exam. Do you see angles? Kids would freak out. No, we're in Scalarville. Who cares? They could have made this any weird shape. They loved that kite shape, though, because it was so symmetrical. Kids would start making up nonsense angles out of sweaty desperation, trying to make it work. But understand, this could be any shape that we want. We don't care, because A is asking us to find potential, a scalar. B is asking us to find a scalar. C is asking us to find a scalar. And D is asking us to find a scalar. So who cares? Kevin, what does A want me to find?
The potential voltage
Keep reading.
at point M.
That's important. Otherwise, I don't know where to... Okay? I'm going to find the voltage right there. You know what I'm cleverly going to call it? I'm going to call it V with a subscripted X, and I'm going to bring in my wings now. Am I going to use the voltage equation with the potential energy in it, or am I going to use the voltage equation, Kevin, with the R in it?
I'm not sure.
You are. You just don't realize that you are. You are. You just don't realize that.
So let me put it on.
Kevin, how do I know? Did they give me distances? Those are radiuses. And it is so obvious that we forget that. Okay? Give me a distance. I'm going to use the one with the R in it. Now, what I should do is find the voltage from this chart. Look up. Everybody look up, please. I should find the voltage. Oh, is there more than one charge? I should label them. Charge 1, charge 2. So, Kevin, what I should do is find the voltage from charge 1 and find the voltage from charge 2. And then I can just add them. Do I have to add them vectorially? No, scalar. But Lena, what do you notice about charge 1 and 2? They are the, loud and proud, What do you notice about R1 and R2? They are the... So for this symmetrical picture, Sarah, I'm just going to find the voltage from charge 1 and double it. I can get away with that, especially it's a scalar. Okay, so I'm just going to make a little note. This is going to be 2 voltage 1, which is going to be 2. Kevin, can you read to me the voltage equation with the R in it? I know it has to have the one with the R in it because they gave me a distance. KQ1 over R1. So it's going to be 2. Lyndon? 2.5 millicoulombs positive. So 2.5 times 10 to the negative 6 all over 0.2. I might be able to do that in my head. 2 times 2.5 is going to be 5. 5 times 9 is 45. 45,000 divided by 0.2. Dividing by 0.2 is the same as timesing by 10 and dividing by 5. 450,000. 90,000? Or am I way off? Double check me. What'd you get? I could be totally off. I was doing a bunch of math in my head there.
I probably did it wrong by 225,000.
225,000? Okay, I was way off. Units, Kevin? Voltage.
Joules.
No,
No.
that's energy. Kevin? Voltage. Volts. Direction.
There's no direction.
Thank you. Okay.
None.
Put a little box around that guy. Mitra, what does B want me to find?
Potential at point 9.
I think I can walk through exactly the same procedure because both distances are identical and both charges are identical. If they weren't, I would find each one separately and just add them together, but let's be clever. So I'm going to say this. The voltage at Y is going to be the voltage from the first one and the voltage from the second one, which is going to be 2 times the voltage. And all I'm going to change is R. It's going to be 2KQ1 over R. I'll call it RY. I really should have called the first one RX instead of R1, but whatever your system you want to come up with. So it's going to be, in fact, you can probably just backspace and edit on your calculator, I'm guessing. 2.5 times 10 to the negative 6 all over. I don't think this will work out evenly. I think, in fact, I'm seeing a yucky repeating decimal. What'd you get, Eric? Give it to me at about 5 sig figs, please.
1.2857 to the 2? No, not that.
I think it's going to be in the 130,000.
Yeah.
Okay, can you read me the digits then? 1.
128,571.4286.
Normally I would round off, but I'm going to use this for the next part, so okay. Tristan, what's C want me to find? So potential difference, the word difference in math means subtract. This is a change in. How are we going to write that? Like this. Now, which one's final, which one's initial? I'm looking at part D, and it looks like we're moving from Y to X. So I think I'm going to say final is X and initial is Y. Is that all right? It's going to be Vx minus Vy. And hopefully you all still have Vy on your calculator so you can use your answer button. So it's going to be 225,000 minus 128,571 ... What'd you get? What is the change in voltage, the potential difference that we're moving this charge through? $96.
96,429.
So I'll write 96,400, and that's voltage, but I'll carry that longer one there. So are you with me so far? Spencer, last thing. What does C want me to find? Sorry, D want me to find.
Work.
Now, put your pencils down for a second and look up. If we had not done part A, part B, and part C, we would go like this. Work equals the change in potential plus the change in kinetic. I would cross out the change in kinetic. I would say potential is, or change in is final minus initial. My final, I would have to find out the potential energy between charge 1 at location Y and my mystery charge, and charge 2 at location Y and my mystery charge. Then I would have to go K, Q1, Q2 at location X. Don't write this down. This is a dumb way to do it. It'd be, no pun intended, a lot of work. I'd be doing about 8 lines. Spencer, what do we find in part C?
Delta V.
Is there an equation that has voltage and potential energy in it?
Yeah.
So, you ready?
Yeah.
Work equals change in potential plus change in kinetic, but I think we're going to assume that the charge begins and ends at rest. Well, don't write this down, just watch. If potential energy equals QV, I think I can safely say that, can I not? And so instead of 8 lines, like I said, of a lot of writing, how big is the charge that we're moving? Spencer, my friend, what does part D say we're moving?
1.25.
I missed the last part.
25.
No, the
Milli.
milli. Oh, thank you. And what's the change in voltage it's going through? The potential difference is what we would call it. Sorry? 96,000. Use your answer button. How much work will it take? How many joules of energy will it require to move this charge from location X to location Y? And you'll notice, Nate, 2 lines as opposed to, oh my goodness, a whole bunch of calculating energies all over the place and ditto marks and combining them and whatnot. What'd you get?
120.5.
120 point.
5. So 121.
Much cleaner. What's voltage, Eric? It's the amount of energy per coulomb at any location. That voltage is created by a planetary charge sending out its electric field. Charged objects in that electric field feel a force. Because they feel a force, they're going to want to move. Because they want to move, they must have energy. Voltage is, well, how much energy per coulomb at that location? But since it combines all of those steps into one concept, it's a lovely shortcut. So if charges begin and end at rest, then work will just be the change in potential, which is the charge times the change in voltage. Example 5 says, prove that if the charge begins and ends at rest, then the work done in moving little q is given by Q delta V. I think we already did on the previous page. I just said this. Look, if potential energy is QV, I said I think it's reasonable to assume that. Yes? So, if you're ever looking at a situation, Lyndon, then where they tell you the voltage at one location and they tell you the voltage at another location and they ask you how much work to move through there, you've got a nice shortcut on your hands. Otherwise, they have to tell you the charges causing the voltage. You have to figure out how much potential energy each one does. Oh, and especially for yucky diagrams like this, and if this was electric field or forces, we would have to add vectors tip to tail. We would need to know angle thetas. Do I see angles? Be breaking things into components. Voltage, it's a scalar. Who cares? Energy, it's a scalar. Who cares? No direction. Here's our summary. The potential, voltage, can be found using the definition. So one way to find voltage, it's defined as the amount of energy per coulomb. That's if you're told the potential energy that a little test charge at a location possesses. That's the voltage at that location. Or if you're told the size of the planetary charge and, Kevin, how far away you are, and R, you can also find the voltage by going K big Q over R squared. Potential energy can be found using last day's equation. Potential energy is K Q1 Q2 over R. However, Eric, if you're lucky, if you happen to know the voltage, potential energy is also QV. Kieran, much less typing. Zip zap. How would we know the voltage, Mr. Dewick? In circuits, if we know the voltage of the battery we're hooking everything up to, then we would know the voltage because it's written on the side of the battery. Oh, that's handy. Note that potential energy and potential are not vectors and have no direction, much like your career goals. So if we have several charges contributing, just add the joules or the volts, and they will try, especially in the ultimate views, you'll see they'll give you these convoluted, hideous-looking diagrams, and you'll freak out at first. Is it scalar? Who cares? They could have put them all over the place. Who cares? As long as they gave me the distances, I don't care what angle those distances are. It's scalar. What's your homework? Don't have a good video for voltage, unfortunately. 1 is good. Two is good. 3 is good. Whoop. 4 is good. How am I going to find the voltage halfway? First of all, halfway between them, what's R going to be? And yeah, and Lena said 2, I'm going to find the voltage from the charge on the left. Probably KQ over R. I'll find the voltage from the charge on the right. I'll include the negative. And I'll just add them up. That's my voltage there. And then B says find the potential energy, QV. 5 is good. So far I haven't skipped anything, I know. 6 is good. 7 is going to be another lesson. I should have moved that to a different lesson. 8 is going to be another lesson. I should have moved that to a different lesson. 9 is good. Skip 10. Skip 11. $12 is good. Skip 13. And we'll pause there, I think. So hopefully you can probably get almost all this done in class. You got 23 minutes, shorter lesson.